अरे सो क्या हो गया? भाई Hello.
Hello, good evening, sir.
Good evening, Narendra. Can
Yeah,
you hear me?
yeah, sir.
And you can see the introductory slide, right?
Okay, sir.
No, no, I'm asking, can you see this? Whatever I have written.
Yes, yes, sir. It is clear.
Okay. And regarding the last time, you mentioned some questions na, about the solutions of assignment 5
Yeah, yeah, sir.
and that last question in assignment 10.
Yeah,
So I have forwarded the email to professors and some students who are students or some staff who are helping with this course.
okay.
So sometime back only I received a reply from Professor Bandopadhyay that they will look into those questions.
Even okay. Thank you, sir.
Mm.
Even in the last assignment problem, we discuss in
Uh,
the solution provided. There is a calculation mistake, sir.
yeah, yeah, I checked that solution na, for assignment number 6, question 10. Na.
10, 10.
I checked the values of U2, HE, U1 are all same, but I think finally they have did some sign mistake, I think.
Yes, yes, sir. And actually, answer is 7195,
But
and that option was not there.
they are getting, I think, 12,000 something. Na?
12,000.
So I think there is some problem of that plus minus somewhere they have done it.
Yeah, yeah. Okay, sir.
Anyway, I hope they'll be getting corrected. I hope, I
Okay.
don't know. I mean, I have done my part. Let's see what happens.
Okay, okay. Thank you, very much, sir.
So,
I had a discuss with you means I am satisfied. Whatever the things I understood the things, it's an enough for me.
yeah, yeah. It's okay that you are raising those doubts. That will help. Actually, I checked the discussion forum after you told na, that these questions have some
Mm,
problems.
mm.
There also some people have raised some queries through mail about similar answers and similar assignment numbers.
So
So,
even sir, in today's any class,
huh?
one Priyanka is there. She also raised the same question.
Huh. I
Priyanka
I
is there.
I saw that there are some 4 5. I mean, I checked it last time last week. So that time there were some 4 5 queries there also. So
Mm.
that means not only you are having such questions,
Yeah, yeah.
other people are also having same doubts, which is
Mm.
good. At least that means people are studying. So
Mm.
anyway, we have, I think Priyanka just joined. So I
Yes.
have forwarded those questions to her.
She is also very serious in this course.
Yeah, that's good. You should keep it up. I think we are halfway. Week,
Oh,
uh, I think total week 12 are there, I think.
okay,
So
sir.
it's like almost half of the course. And you have maintained good enthusiasm till now. So
Yeah.
just keep it till the end. And I'm sure you'll be getting, whatever is your objective. If you study properly, you'll achieve it. No worries there. So anyway,
Okay,
uh, so what I think, I saw the previous classes of last week. So essentially, second law of thermodynamics is started. But what I've realized is I'm spending too much time on class revision,
yeah,
and therefore problems are, you know, we are extending about 30 minutes or so.
yeah.
So today I'll just keep it brief. I'll not go into details, but I'll just make a list of things that you should know from the theory of this week's class. Some of them are covered by professor in class in the video lectures, and if not, you should look it up. If you have any queries, you can call me, or we can talk in the next lecture also, or next discussion class also. So first of all, if we start, uh, the first thing you should ask yourself is why the second law of thermodynamics. I'm writing TD, which is for thermodynamics, short form. Just don't get confused. Why second law of thermodynamics is required. And oh, I should not use so much abbreviation. I'll put. uh, So this is the first basic question. Why are we doing this? Why do we need? We have a first law. Why do we need second law? And I think Professor Suman Chakravarti also explained properly. I mean, completely that there are very serious implication of this law, not only in classical thermodynamics, but almost wherever energy or heat interaction is there, you can use second law of thermodynamics, and that second law, which is actually it is called as directional law somewhere. I mean, these are terms that you'll see in competitive exams. Directional law, some will call it qualitative law. First law they'll call first law they'll call it as quantitative law, and second law they'll call it as qualitative law. So essentially the idea is that only that first law essentially gives you the energy balance. It doesn't tell you whether the heat should be flowing like the direction of spontaneous energy interaction. So uh, first law is incomplete in that sense. Second law completes it. So that's the basic. If anyone asks you why you are doing, and if you have to give one liner answer, that is the answer, because it gives you the sense of spontaneous direction of the system. I mean, in which the system will spontaneously proceed without any spontaneous. That means itself that no external thing is required. It will spontaneously go there. So that is it, and some other nuances are also there. For example, uh, we'll take some examples of thermodynamic devices, or devices which operate on thermodynamic cycles. There you can use second law. I mean, till this assignment, the whole thing is not there. I would say only half of the part is covered as of yet. So maybe by next weekend or next week's class end, you'll you'll understand the whole second law and how to apply it for cyclic devices. Uh, then one more thing is very crucial that comes out of this law is uh, mm, hmm, it is, I mean, this concept of absolute temperature scale. So if you go for any interview or anything, I mean, it's if you say your thermodynamics is a favorite subject or something, you should expect such questions. In maybe in competitive exams like GATE or ISRO or anything, or PSC or something. This may not be that important, but if you are appearing for any interview, you should absolutely know this if you are going to give thermodynamics as one of the subject. Basically, this uh, absolute temperature scale, it's very important. Nowadays, we deal in Kelvin, but there was a time, there was a big or long time where when the Kelvin scale was not there, people used to follow their own scale. Some used to follow water steam length scale, I mean temperature scale. So basically, water at ambient pressure, when ice forms or formation starts, that will be 0 degree Celsius. When the steam or evaporation uh, or phase change is complete or starts or complete, because that's a constant temperature process. That point they used to take as steam point, and they used to assign value 0 to the ice point, 100 to the steam point, and divide in between the scale as linear scale. That was one scale. Some used to take some other material which is called as this thermometric substance. So you should also know about thermometric substance or thermometric property. Uh, Substance is not that a good word, because sometimes length change or volume change, such properties were also used for temperature measurement. So there was no standard, or like in the sense people did not know any standard, or they did not have any way to assign it to a standard. So that's when this temperature scale given by absolute temperature scale is there. The detailed discussion was there in the professor's lecture. I think you should see it again and again if you are not understanding it. But this is very important concept, absolute temperature scale. Uh, there are different type of explanations given. I remember when I was studying, there was one explanation in which, uh, uh, like, I mean, it's the same explanation generally given. They'll give you two heat engines operating in series, and based on that, uh, they'll define efficiency as a function of temperature, which should be satisfying certain properties. Uh, and the easiest choice of that is linear temperature, the function of temperature which is linear, and that's what Kelvin did. I mean, this this is named after Kelvin because he was a great scientist and he assumed that function to be linear. You can assume anything, but since it's a norm nowadays, you should take it only as an exercise. In practicality, the linear temperature function is assumed. So that is there. You should know this. If you have uh, explore it on your own. If you have any problems or doubts in this, you can ask me later, or maybe now only. If you have any problems, you can just ask. Uh, then there is the concept of heat engine, uh, refrigerator, heat pump. You should be very clear about this. Normally, if nothing is mentioned, we assume it as a reversible heat engine or reversible heat pump or refrigerator. But you should understand that this reversible thing, it's an theoretical abstract. In real life, it will not be completely reversible. So that is one thing you should understand. We should know the functionalities of all this, where heat engine is used, where these two are used. This is basically work producing device, and these are work consuming devices. And depending on your desired effect, you classify it as a refrigerator or a heat pump. Uh, then and keep in mind all these three things, they work in they operate in a cycle. So that was why when in classes, even the professor was showing them, he used to give this arrow. That arrow signifies it's a cyclic device. It's not a 1 to 2 or 2 to 3. It's 1 to 2, then 2 to 1. So it's a cycle. The arrow, the direction of arrow doesn't matter. You can keep it whatever you want. In some books, the arrow is not given, but I feel this is a good way to keep check that it's a cyclic device. So that is one thing you should, whenever you define these type of things, you should mention what are that they are operating in cycle. Many times people forget this. That's why I'm telling you. It happens when you are giving interview. Uh, then there is PMM1, PMM2. I think PMM3 is also there, but 3 is not in this second law's purview. It's, I think, related to third law of thermodynamics. PMM1 is basically, if you want to know what is PMM, basically it means perpetual motion machine. So as the name suggests, perpetual means forever, non-ending type. So machine which works without ending or continuously, but it violates some of the thermodynamic principles. The second law is called as PMM, and there are two statements and their equivalence of Kelvin Planck and Clausius statement statements for second law. I mean, students usually know these statements separately. That is also required. But what I feel, you should also know the equivalence of these two statements, because many a times these type of questions are asked in interviews or even in common subjective exams. If you are preparing for civils or ESE, I don't know what is going on in ESE right now, but any subjective paper, if you are going to appear, there is a chance that from thermodynamics such uh, conceptual question may come. So you should know the statements individually and how to derive their equivalence. I think professor showed one case, but the second case was left for you to do as an exercise. Even if you haven't, you can just type in YouTube equivalence of these two statements. You'll get number of videos and at least watch one of them, which is the shortest, I guess. Anyway, so yeah. Uh, Other than that, there was discussion on uh, Carnot's theorem. Essentially, uh, and its corollary. One corollary is also there. I forgot its corollary. I'll write consequence. I forgot the spelling of corollary. It's corollary or corollary. Anyway, so basically, what Carnot's theorem says is, if you have two heat engines or heat pumps, let's say heat engine, the efficiency of reversible heat engine will be higher than the irreversible heat engine. Uh, and I don't know whether you know or not, but Carnot was not. I mean, you can look into history of Carnot as well. It's an interesting personality. He was, I think, engineer. He was not a professor or anything. He was engineer, French, I guess. Huh. So anyway, so he gave one theorem, and its corollary is, or the consequence of it is that uh, you know this efficiency of reversible heat engine is independent of the working fluid. So based on that only, you further go and define absolute scale of for temperature. And the last thing will be reversibility of a process. Uh, it can be internally reversible and it can be externally reversible. And if it is both, if it is internally as well as externally reversible, we call it as a reversible process. If not, then it's a reversible process. In Carnot cycle, if you remember, Carnot cycle is two constant temperature process and I think two adiabatic, reversible adiabatic and reversible isothermal. Such four cycles, four processes make Carnot cycle. One more question, which is very commonly asked in interviews or common entrance exams also. Plot Carnot cycle on PV plot or TS plot for phase change as well as no phase change. So these two questions are asked commonly. You should know this. Please do yourself a favor and prepare for this now only, because it's a very simple question, but if you don't know, you'll not get it in the exam. So that's one thing. Then there are some factors which destroy the reversibility of the process, uh, which cause irreversibility. Uh, I mean, for internal irreversibility, there are like list of some 3-4 factors, but essentially you should know friction is the main culprit here. If it's mechanical friction, we call it as friction. But if it's related to electrical or magnetic, we call it hysteresis or eddy losses, something like that. So friction is the main culprit for internal things, internal irreversibilities, and like unconstrained volume gas expansion or mixing of two gases. So those type of special cases are also there which can cause irreversibility. And external irreversibility is due to temperature difference delta T across the boundaries of your system and surrounding. So this much theory was there in today's class. One more question which is very trivial if you feel you can spend some time on it or not. Triple point of water. Uh, you should know the temperature which is 0.01 degree Celsius uh, equal to 273.16 Kelvin. This is, believe it or not, this was a question in the very recent GATE exam, I think. I mean, maybe GATE or ESC, I don't remember, but this directly was asked. If you know, if you know. If you know, then you know it. Otherwise, you'll not guess in the exam. And there is a pressure associated with this also, I think 0.61 kPa. Something like that. Maybe it's not correct up to the second or third digit, but it's around 600 kPa. So you should know that value also. 600 Pascal. So yeah, that's it. I think if even if I did not want to, but I spent let's say 20 minutes on this. Anyway, I mean this discussion is required if we are going to talk about second law of thermodynamics. If not, then it's just a mechanical discussion, which I don't like. Anyway. So we'll start with some problems. During that only we'll discuss next things like efficiency, COP. Yeah. Anyway, if I forget, there is one more question that I want to ask to you or uh, whoever will be watching it later. uh, Generally, people know that efficiency generally lies between 0 to 1. And lower limit is 0 because I mean it's trivial, but lower limit is 0 and upper limit is 1. But second law of thermodynamics doesn't allow it to go to 1, and so it limits the upper limit for efficiency. For efficiency is constrained by second law. Similarly, uh, this COP, coefficient of performance for refrigerator or heat pump, it is also upper bounded by the definition of it. So these things you know. But my question is, what is lower bound or lower limit for COP, coefficient of performance? And this question is very tricky. It was asked, I mean, I know it was asked in some exams, interviews. If they for like, let's say if you have a habit of solving this for competitive exam, I'll give you some values. So uh, the essentially everyone knows efficiency is less than 1, and if you solve RAC problems, refrigeration and air conditioning problems, there the COP is always above 1. It will be around 2 3 somewhere there, because we generally solve VCRS, vapor compression refrigeration cycle. But that is not always true. I mean the COP is not always greater than 1. uh, COP can be less than 1, which is observed for VARS, vapor absorption refrigeration cycles or systems. So that's what I mean. The whole point of this question was that only. Lower limit of the COP is not bounded by 1; it is bounded by 0. I mean, if I am asking this question only for thermodynamics students, they will maybe know the answer. But after you solve the RAC problems, it is very confusing. That's why I'm telling you here that COP can be less than 1. It is not necessary for it to be always greater than 1. So please keep that thing also in mind. And we'll go to the first problem then. Uh, Actually, sorry for my handwriting. I feel it is going slanted. It is tilted upwards. Maybe because my sitting position or something. But anyway, as long as you're able to see, I think it should be fine. First question will start. This is very classical problem of cascading. cycles. So what generally happens is second law tells you that you need to reject some heat in order to operate the heat engine in cycle, continuous work production, right? So what people thought, let's say if you have a heat source, and many times definition of heat source is also asked, or heat source or heat sinks. Heat source or sink will have uh, heat capacity tending to infinity. That is the definition. If you tell this much, it is fine. Anyway, so let's say if you have this thing, it produces, let's say, some work W1, and it is taking QH from the heat source operating in a cycle. This is a reversible heat engine, and it has to reject some QL which is greater than 0 by second law of thermodynamics. So instead of, generally there will be one temperature sink at lower temperature TL. But what people thought, instead of doing this way, why should we reject the heat? Why should we even do that? We can put another heat engine and extract some work possible, right? So this will be heat, second heat engine. And finally, eventually, you'll have to reject something. So you can't do this, tend this to 0, right? Otherwise, the second law is not satisfied there. But in later classes, you'll see about the availability and all. So there you'll realize that as the temperature of heat source decreases, the available energy also decreases, and that's why work output is also not that good. So it's not worth putting heat engine when the temperature of the source is too low, because the work potential is not there. Maybe it will come later. So anyway, so now you put two heat engines here. So generally some intermediate QM will be there, and lastly QL. So this is called as cascading cycle with two heat engines. There can be three, there can be four, but generally typically two are there, because up to 3 and 4 if you go, it's not worth it. You'll not get efficient heat output. So that investment is bad. So typically this question is asked. I checked previous gate years also, previous gate questions also. So in one of the gate exam, I think directly this formula was asked. For cascading cycle, what is the efficiency formula? There they call this first cycle as topping cycle, and second cycle as bottoming cycle. I mean, this nomenclature is not that hard and fast, but it is generally written in this way. So, one second, I'll just trying to figure out which question was this. Anyway, I'm not able to find but I know this question was asked in GATE exam. The efficiency of first cycle is efficiency in eta 1 and second is eta 2. And then the efficiency of overall cycle when these two cycles are put in the series is asked. It's a very common question. And this was, so what you do, you start, uh, like you assume this, it is given here reversible, but even if not, you assume it as reversible. And I hope you'll know, we'll assume this intermediate heat at some Tm temperature. If you do that, you can write Q1 as 1 minus Tm by Th. This can be again written as 1 minus Qm by Qh, right? So or in terms of work, you can write it at W by QH. These are all three things that you can write. So this is one. And the second part, which is the similar thing for second cycle, you can write 1 minus T L by Tm. In terms of work done, it will be net output upon input, which is Qm. So now you need to write the overall efficiency, and overall efficiency will be, I will just write it as O, eta O. So what is the total output of the cycle? W1 plus W2. And how much heat did you give? QH. So just separate these two terms. That will be half part of your solution. So you can see this is eta 1 plus W2 by QH. So now eta 2 is W2 by QM. So what you do? You multiply the second term by QM and divide it by QM. So if you do that, W2 by QM will become eta 2, and you will have QM by QH. This term will be there. So then again you do from energy balance, or not even energy balance. You can use this equation, right? QM by QH will be 1 minus eta 1. So this will be like this, and finally eta 1 plus eta 2 minus eta 1 eta 2. So many a times people just mug up this formula. That also works for MCQs, but you should know how it came. And don't mind asking, don't mind me asking. Uh, for example, if efficiency of topping cycle was 0.4 and efficiency of bottoming cycle was 0.3, the overall efficiency will be 0.4 plus 0.3 minus 0.12, if I'm not wrong. So 0.7 minus 0.12. So it will be 0.58. I think I have not done any mistake here. So yeah. So you see, the point of doing this simple exercise was, if you had just put one reversible heat engine, uh, you had 40% efficiency. But if you put two, your efficiency is almost 60%, so 20% more. So, like, the trade-off here is you are getting 20% more efficiency, but you are putting a new reversible heat engine in your system. So, as long as this trade-off is giving you higher efficiency, for like the increase in the efficiency is compensated by increase in the cost of putting a new heat engine in your system, it's worth it. If not, you stop. So what will happen if you put, let's say, 3-4 reversible heat engines? This overall efficiency will be not, like, for addition of subsequent heat engines, the increment in efficiency will not be that significant. So at that point, you say ki, this is the optimum amount of heat engines in my cascading cycle, and we stop them. Another way of stopping is also the availability, but if you don't know that concept, and I'm assuming, like, let's be naive and do this way. So anyway, that was the point of doing this calculation. So yeah, and the eta 2, which is deliberately taken lower than eta 1. I mean, I can take eta 2 as 0.5, but it will not be 0.5. It should be less than 0.4. Intuitively, you should understand this by now, that when your delta T between the heat engine endpoints decreases, uh, your this thing also decreases efficiency. So don't take some absurd values like eta 1 as 0.4 and eta 2 as 0.6. That is absurd. So yeah, I think that is about that question. Then there is one typical question that is asked from this topic is, uh,
Sir, hello, sir.
ha, Narendra.
Mhm. Sir, there is a similar question in the assignment 7 to calculate the overall efficiency, but it is for the refrigerator.
Efficiency for refrigerator.
No, 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 COP, COP.
Okay.
Already I have solved.
Actually, the thing is, I am not supposed to take assignment questions.
No,
That's
no,
why.
no, sir. I'm not an. I'm just an saying there is
Uh,
a similar question in the assignment, and but it
first,
is on
first,
the refrigerator.
first question
And
only.
already I got the answer.
Yeah, yeah. So the point is, for cascading cycle with the heat engines, you should know this formula.
Yeah.
And for cascading cycle with the refrigerator or heat pump, you should know that other formula.
Yes, sir. I got the
So
answer, sir.
yeah, that is good. But keep in mind, like you by heart this formula, forget. That's it.
Yeah.
So yeah, good. I think you people should be able to. This COP derivation is slightly tedious, but I think
Yeah.
people can do it. So anyway, the next one type of question that is typically asked from this area is what they'll tell is there is a room and you need to maintain that room at certain temperature during summer and winter using heat pump and refrigerator. Like one heat pump will be there, which will act as heat pump during summer. Oh, sorry, during winter, and it will act as refrigerator during summer. So that type of question is very typical. So I'll take one example of this also. Uh, so this is a two-part question. So what is there during summer? I'll just I'll not write complete question. I'll just give you the data in two separate things. So as I told you, there is one heat pump which heats the house in winter and cools it by acting as a refrigerator in summer. So let's say summer, it is a heat. It's a refrigerator. So the lower temperature or the lower temperature source will be a room. It is taking heat from your room, doing some work. No, not doing. It requires some work. This is a refrigerator. We assume it as a reversible for this time. Okay, and it will reject the heat. It will be rejecting heat to ambient. That will be your heat sink where the heat will be dumped. So this is the system during summer, and you know, in summer you need to maintain this temperature of room at 25 degrees Celsius. That is your objective. And let's draw for winter as well. In winter you'll be having the same arrangement, but here the things will change. In winter you need to heat the house, right, to keep it warm. So this will become your room, and your ambient will be cold here, and you'll take heat from the ambient and also work done, external work done, and you'll dump that heat in the room to make it warm. So this is heat pump reversible again. And the objective is in winter you need to maintain it at 20 degrees Celsius. This is your objective. And in the question it is mentioned that the heat transfer through the like from the walls of the room to the ambient is estimated at 2400 kilojoule per hour. So Q loss is given as 2400 kilojoule per hour per delta T. I should not write this way, it may be confusing. Per hour per degree delta T temperature difference between room and ambient. So basically, this 2400 kilojoule per hour, it's not a constant. it's for 1 delta T, 1 degree Celsius temperature difference. If it's 10 degrees Celsius, then it will be 24,000 kilojoule per hour. So that is the meaning of this. Now, in summer, this Q loss is actually your objective. I mean, this Q loss will be equal to QL, Q capital L here, because that much heat you need to reject, and that will be dumped into the ambient. But in winter, this is not a good idea. I mean, this heat loss is actually your loss. So this will be your Q loss. It is getting lost from room to ambient, and from first law of thermodynamics, it will be equal to QH. Assuming no losses, we are neglecting other losses. There will be some losses, but for this example, we are neglecting them. So this is your whole system. Now the first question is, if T ambient is 0 degree Celsius, what is the minimum power required? So now there are two questions. One is, which thing you'll use? You'll use it summer or winter? I mean, it's very obvious, but you'll not have 0 degree Celsius in summer. So this is a winter case. This much you should be able to recognize. And the minimum power. So here it is asking power because your heat loss is kilojoule per hour. So all these quantities, Q and W's, shown in these two figures, they are in kilowatts or watts. So that is also there. And since it's a winter, it will be a heat pump, which is shown in the second figure. So now how will you calculate the minimum power required? Once you understand the system, it will be easier because now you have your system. You know QH is, sorry. Now you can calculate delta T between room and ambient. It will be your target of room temperature is 20 degrees Celsius. So 20 minus 0 ambient temperature, this is 20 degrees Celsius. So therefore your Q loss will be 2400 into 20 kilojoule per hour. So this is one thing, and this is equal to QH. Now you need to find W. So since it's a heat pump, you should know COP formula, which is desired effect upon work input. So work input is W, and desired effect, since it's a heat pump, it will be QH. And since it's a reversible heat pump, you can write it in terms of temperatures, absolute temperatures as well. That will be TH by TH minus TL. So in this equation, you know QH, you know TH, which is 20 degrees Celsius, you know TL, which is 0. So W will be your unknown, and it's fairly simple to calculate. It will be 48,000 into delta T 20 by TH, which is 20. So in Kelvin, it will be 293 Kelvin. So this should be your answer. Yeah. So if you do this calculation, you should get 0.91 kilowatt. The numerical value is not that important. You should know how to solve these questions. That is more important. This is the first part. Here itself, I'll give you, I mean, this was given by professor also in the class. So there is one relation of COP HP for reversible heat pump, which is TH by TH minus TL, and COP for reversible refrigeration will be TL by TH minus TL. So that there is one relation between COP of HP and COP of R, right, operating between same temperature limits. This is, you can derive it from here itself. What you can do, take this term cop R, add 1 on both sides. So this will become TH minus TL plus TL by TH minus TL, right? So this becomes TH by TH minus TL. So which is nothing but cop of reversible heat pump. So yeah, I mean this was given to you in class also, but you can derive it very easily. And in exam, if you forget what was the formula, believe me, that happens under the pressure of time. But if you do, just do one thing: add 1 to the formula and see if it is giving the derivation for cop of the second device. If you add 1 to this cop of HP, you'll get nothing. So that is not the correct answer. So basically add 1 to the cop of refrigerator. This is a trick that you can remember maybe for the GATE exam. Coming back to the question now, since the question first part was for winter, I think the second part will be for summer. Yeah, the second part is slightly different. Uh, it is asked that let's say you are using for same work done. I mean here this 0.91 kilowatt, it was used for uh, heat pump, but now in summer it acts as refrigerator and you are doing same work done. What will be the what is minimum ambient temperature for your refrigerator, no, for your heat pump to operate? This is the question. So now you do one thing, you write op for your heat pump, which will be QH by W, TH by TH minus TL. I think I'm doing some mistake here. Yeah, in summer it's a refrigerator, not heat pump. So if it's a refrigerator, your desired effect is QL and it is also TL. So now uh, you what do you know? You know W because it was given in the question that it is same. You know QL, right? Because that was your Q loss. But now you don't know the delta T. So basically, if you write this thing, you'll be having this kilojoule per hour into some T minimum ambient minus 25 degrees Celsius, which is your room temperature. To avoid confusion, I'll keep everything in Kelvin only. So this will be 25 degrees Celsius, which is 298 Kelvin. Work done will be 0.91. I'm keeping it in kilowatt. So this is kilojoule per second. But this guy was kilojoule per hour. So you need to convert this also. Uh, Essentially, you need to divide it by 3600. So I can write it here itself. So now the units are matched. And this should be equal to TL. TL is again 298. T minimum of ambient is unknown and 298. So you have one equation, one unknown, right? So you should be able to solve it. But the catch is this becomes a quadratic equation. So if you simplify 834, any, uh, so essentially you have minimum ambient temperature 298 square equal to 298 into 0.91 into 3 by 2. So I can directly write it as 1.5. So now you can take square root on both sides and take a positive root, uh, because this value is I think greater than 298, so you can't take the negative root when you take the square root. You have to take the positive root, and that will give you the maximum limit. uh, I mean, uh, the upper bound, since you are taking this as equal, that will, I think I should rephrase the question, my bad. It should be maximum temperature. So uh, if you solve this, I'll give you the answer. Maybe you can verify yourself. It will be 318.32 Kelvin, which is 45 point, let's say 2 degrees Celsius. So roughly 45 degrees Celsius. So the basically, if your ambient temperature is more than that, this system is irrealistic. Second law does not allow this system, allow such system. But if the ambient temperature is less than 45 and more than 25, such system can be there. So yeah, such question is very common from this part. We are, I think, already 7, but we started, let's say, 5-10 minutes late. So one more question is there. Hmm, let me check if I have some other questions. Hmm. This cascading cycle I was telling you about, in which two heat engines are arranged in series. If you check the GATE 2015 mechanical question paper, no, there is one example which is based on that, 1 mark. Uh, Such examples you'll find a lot of times. I'm just telling you a few examples here. I don't have time to check everything here, but that type of questions are very common. And this COP relation, COP R plus 1 equal to COP HP, it was also asked in GATE. It is an old question, 95. But anyway, you should know. We'll take one more question. Uh, Generally, what they do, hmm, this is GATE 2004. Uh, there is one typical type of uh, problem set you'll observe if you see some questions in previous GATE or in some assignment also you'll see here. It is related to solar collector. Generally, to find its area, uh, what they will do is they will give you at what rate the heat from the sun is coming. I'm giving you one example, solar radiation basically. So instead of sun, I'll write the solar rate of heat coming from the solar radiation. This is 2004 GATE question for the 2 marks. So it is like this. And efficiency, overall efficiency of the solar collector and that conversion system is 50%. Uh, I mean the efficiency from collecting the heat and heating it, the working fluid. So that is 50%. The fluid is heated at 350 Kelvin, and it drives the heat engine. So basically, fluid comes here. Solar radiation is added to it at 350 Kelvin. Then it drives the heat engine, and it rejects the heat after producing some work at 313 Kelvin. And the power output. One second. The power output, which is W dot from this heat engine, is 2.5 kilowatt. So, and the question to find is minimum surface area for solar collector. So see, this is a flux, so it's in kilowatt per meter square. So you need to find how much minimum area is required. So this comes in handy when you are designing a solar power plant. So you need to have certain area for solar collectors to collect the solar radiation, which is sufficient enough to do some work. So this type of questions are very typical from this part. If you see, it's not that difficult question. You just need to construct one heat engine uh, that will be giving you some work done. TH and TL are known to you. Work done is given, and the keyword is minimum surface area. So basically, minimum surface area, that means maximum efficiency of that heat engine. So you know maximum efficiency will be 1 minus TL by TH, right? So you know TLTH will get the max efficiency value, and it should be equal to the heat supplied, work done upon heat supplied. So here you know this side, you know work done, you'll find out the QH value. So if you do the calculations, mm, you'll get some QH value. Uh, I don't have that value at this point with me, but this is the value assuming there is no loss of heat coming from the sun to the this thing, uh, the heat engine. But the 50% loss is also there. So this QH will be nothing but half of, like, the 50% of Q solar, and Q solar is given as 0.6, so this will become zero point 0.3 kilowatt per meter square into some area. So this will be your unknown. So from here you get the area, which is minimum. So if you do this calculation, you should get 79.4 meter square. So this type of question I saw in a couple of places, so I thought I'll give you, because it adds a different kind of flavor to the problem setting. Uh, maybe solar receiver and all those type of things are involved. One thing to note here, this is minimum area. So if you are planning to do a solar power plant construction somewhere, if you don't have this much area for solar collector, even the theoretical, assuming no loss condition, ekdam ideal condition, then also you will not get the desired output of, 2.5 kilowatt. And this is minimum. The actual area will be more than this. So for that, you'll need to consider different losses. Here you assumed it as reversible heat engine, right? In actual, it will be not. So those type of things, if you consider, you'll get even more area, let's say 100 meter square. So now second thing you should understand is, to get 2.5 kilowatt of energy output, continuous work output, you require 100 meter square area. I mean, if you can imagine 1 meter square, that is itself is very big. Uh, I mean, typically 100. So basically, the thing is, one more conclusion is, solar energy is highly dilute form of renewable energy. So this is also one consequence of all these things you should understand. If some of you go on, in future work on renewable energy and energy storage, like me, then you'll understand these things. Anyway, moving on. We'll take one last problem. This is a slightly different problem, but I will say not that different. If you can solve, uh, if you are able to understand till now what we have done, you'll be able to solve this also. So, one second. Yeah, uh, there is a tank, thermal storage tank. This is a sensible heat storage. If you don't know, sensible heat storage is basically storing the heat by the virtue of temperature difference of the storage medium. So here you have rocks, granite rocks. Mass of this uh, thermal storage, let's say bed, we'll call it bed. Mass is 5.5 tons, and it is heated. Like initial temperature will be 400 Kelvin. So if you can do the calculation, it will be approximately 123 degrees Celsius. So it's quite hot. This is heated using solar radiation. So there is a sun and it hits this bed and it reaches the temperature of 400. Then the sun sets. It's not there now. So you have a heat source. You put it. You run a heat engine using it. Uh, and it rejects some of, so it will receive some heat from the thermal storage bed. It will reject its heat to the ambient, and it will produce some work output during this process. So this is a cyclic device. So this is the whole setup. Ambient temperature is 290 Kelvin, which is a typical ambient temperature. Cp of the salt or the rock is given as 0.89 kilojoule per kg Kelvin. So to find one, you need to find uh, QH max. That means maximum heat output from the storage bed or the granite rocks, and efficiency of heat engine at T equal to 0 or start is what. So now the calculations are simple only, but you should understand why such question is given. This is a very practical system. You may come across it if you are, anyway related to a thermal storage device. So as I told you, solar energy or solar thermal energy is a dilute form of energy, renewable energy. So you can't give such 100-meter square type of area always. Uh, and even if you do, the next problem is the energy, solar energy is not continuous. During night time, you will not have solar energy, right? So that time you use some storage device. This thermal storage device is quite inefficient. I mean, there are efficient ways of storing the solar thermal energy, but for this problem, we are taking the rocks. We are just hitting the rocks and we are extracting some work output from it when the sun is not available. So that's the question. Now, the first question is, what is the maximum amount of heat that you can extract from the rocks, which is QH max. So initially the temperature is 400 Kelvin, and let's say you started the heat engine. Now the difference between the problems that we saw so far and this problem is your heat source is not having specific or heat capacity of tending to infinity. This is a finite heat capacity source because the mass is 5.5 tons and the temperature is also 400 Kelvin. Sorry, not temperature, the CP value is also some finite value. So heat capacity, if you calculate for this heat source, which will be MCP, that will be 5500 into 0.89 kilojoule per uh, Kelvin. So this is a finite amount of heat capacity. So this QH that you are getting from the heat source, that is also not constant value. Till now we are taking it as a constant value because your heat source was having infinite heat capacity. So whatever amount of heat you take from the source, its temperature is not decreasing or not changing, and therefore you are getting constant heat output from the source. In practical, you can consider sun as a uh, heat source with infinite heat capacity. Whatever amount of heat you take from the sun, its temperature will not change because of that. It can change because of other things, but it will not change because of the amount of heat that is you're taking from the sun. But this is a practical case where you have a finite amount of heat capacity heat source. In such case, as you may know, maximum heat that you can extract will be MCP, initial temperature minus ambient temperature. You can't go below ambient temperature because I mean that violates the second law of thermodynamics itself. So you can do this calculation and you should get the value of 538,450 kilojoule. We can write it in megajoule also, just for the sake of short answer. So this much amount of heat it can give you, but the problem is this much amount of heat is not at constant temperature. So you can't use that formula of efficiency of 1 minus TL by TH for complete process of heat transfer. I mean, just write it complete process. Because at each point of time, you are receiving some dQH, which will be MCP, assuming it is coming from the whole mass, it will be at dTH. So your actual efficiency, if you do the calculation, it should be dW integrated over the whole process. With respect to time, it will come because of the units and your heat supplied. This will be also be an integral. How to evaluate integral, that's a different ball game altogether. No need to go there. But the point that I'm trying to convince here is you can't use such simple formula here because of the nature of the heat source. But in question, if you see what is asked is at the beginning, what is the efficiency? So there you can just assume reversible heat engine at start for small time, which is let's say very small value of time starting from 0. In that case, you can write initial efficiency as 1 minus TL by TH. So 1 minus TL is 293 Kelvin, and initially I think the temperature was 400 Kelvin. So if your efficiency will be 70 to 27.5%, and you can see the efficiency here itself is very low because there is not much difference between TL and TH. That is another thing you'll study in the next class maybe or the next assignment time. If the delta T or the difference between TH and TL is more, your efficiency will be higher. That is one thing. Anyway, and just for the sake of discussing, what will be the efficiency of your heat engine at the end? So end means your TH will become T ambient, which will be 293 Kelvin. So efficiency at the end will be 1 minus 293 by 293 0. So basically there is no no work output when your source temperature attains the ambient temperature. So this was one question. The key takeaway of this question was you should consider uh, you know type of heat source that you are dealing with. Typically, if it is an infinite heat capacity heat source, that is fine. But if it's a finite heat capacity heat source, you may not be able to apply all the formula that you have learned so far. You'll have to go with the differential calculation there. So anyway, so that was the point. There is one more thing, maybe not now, maybe later I can discuss. Uh, Similar thing only where you have a finite heat source and finite, I mean, two bodies who are not having infinite heat capacity. Finite heat capacity, heat source and heat sink. Here, heat source was having finite heat capacity, right? But your ambient was at still constant temperature of 290 Kelvin. But one more variation for uh, one more variation can be where your heat source is also finite capacity and your heat sink is also finite capacity. There, how do you solve the how do you apply the first law and second law, and how do you find the efficiency and all? That can be also a variation. Uh, right now, I don't think we have enough time. Uh, Maybe uh, give me a couple of seconds or minutes. If I am able to find that solution, I have it somewhere. If I can find, I'll share with you. Uh, hmm, 1 second. It was in my old notes when I was preparing for GATE and all. So basically, what happens when you have both heat source and heat sink at which are having finite heat capacity? You first calculate the uh, final temperature from the first law. So 1 second, I think I should be able to find it. Hmm. 1 second, I'm not able to find the whole this thing. Anyway, I think it's getting late now. Maybe next time we can discuss. Uh, but I did you understand my point? Uh, like when you have uh, like I'll just draw some simple thing. We'll discuss next time. Don't worry. I know it's getting late. Let's say you have a heat source at temperature T1 and some mass M with some specific capacity C, and there is a heat engine which is producing work by taking Q from the hot source, rejecting some work, some QL to a heat sink which is at T2, some mass and some heat capacity. So, and obviously T1 is greater than T2 at start. Then only we can have a practical system. So if you have such system, so this is both are finite heat capacity. So if you have such system, how will you do this thing? What they call? How will you calculate what is the maximum work output from such system? That is a question. I give it to you as a homework, or maybe it's a friendly assignment. I'm not your professor, so I can't give you homework. But anyway, so what will happen? I'll just explain this process to you. Eventually, the both of this, if you apply first law, initial energy is mcp t1 plus m dash c dash t2, and finally the whole mass, and it will be at some final temperature Tf. So from first law you can calculate Tf. That is fine. That you can do anyway. But how will you find the maximum work done possible from this system? Because work done will be high at the start because the delta T is higher. T1 is greater than T2. But eventually this delta T will decrease and your work output from the heat engine will also decrease. So you need to basically find the total work done during that process and maximum amount of that work done. So basically you are assuming reversible heat engineer. So this is a question. I will leave it because it needs some sort of extra discussion about the entropy property as well. So maybe it's not a right time to discuss here, but I'll try to discuss it maybe next time or the next to next time. If I forget, please remind me, and if any one of you can solve it, that is fine. But this type of question you should have some idea because you may find it in some subjective exam or some interview, and it's good for testing your knowledge about second law as well. Because the typically infinite heat source, heat sinks, everyone can solve. Infinite heat source and finite heat sink, or vice versa, that also people can solve. But when both are finite, that is when the things become slightly dubious. So, okay, we'll take that up in the subsequent classes. So, I think we should stop now. If any one of you have any question about this class or assignments or anything, you can tell me now. If not, we'll close.
Sir, hello, sir.
Narendra.
Again, in the assignment 10A7, in one of the question, no doubt I have solved it and I got the answer also. That answer is 49 lakh 37,142 is the correct answer. But in the option, answer is given round figure 49,037,000.
Last question, huh? 10th question.
Last, and there is one more that none of the above that option is also available.
Okay.
There is a just
We'll quickly solve this. It was, I mean, it is a fire, coal-fired power plant, huh? So it is
yeah,
basically
yes, sir.
a heat engine type only.
Yeah, already solved, sir. I getting the answer. So may I select the round value? Yeah, none of them. There is a difference of 142.
Okay, 1 second. If some people see it later, we'll just solve it. Uh, this what is this kilojoule per kg? Huh? I'll just write it as C. And what is it asked? How much coal is used per day? So mass of coal
Mass per day.
kg per day. This is asked. Huh?
Yes.
So yeah. Okay, this
Sir,
is.
it is coming 49 lakhs 37,142.
I should not have written it as heat engine. Sorry, my bad. It is not a heat engine. It's a. I mean, anyway, let's not go there. W net by Q supplied, right?
Yes, sir.
W net is 500. This is unknown. I'll write as Q. It will be 35 by 100. So 7 by 20. So Q will be 10,000 by 7, right? It is MC. So M will be 10,000 by 7 into C. Oh, sorry, 1 by C. So that will be 1 by 25,000, right? It is in megajoule. Oh, sorry. So there will be a factor of 10 to the power 3 somewhere, right? Megawatt, sorry. So it is like this. If I have not done any mistake. Mm, by 7. So yeah, this goes off. So basically it is 10,000 by. Oh, I can do this also, right? 5. It will be 2,000. It will be 400. 400 by 7. Bapre. Where did I go wrong? One second, I'll use calculator. 0.35. Mm, divided by 7. Bapre. Narendra, where? अच्छा
They,
per day,
are,
yeah.
sir, already I have calculated that.
अरे नहीं, I am calculating per second.
Uh,
This is a per second value, right? I mean this
per
is
day we have to calculate.
megawatt, so this is in kilowatts. So 400 by 7 per second, kilojoule. I mean, uh, this is a kilowatt. So basically, you have to multiply by
Uh,
400 by 2 per second. So in 1 hour, there are
33600 into
24.
24.
So if you do this, you should get 4937142.
Yeah,
Uh, yeah, I mean, I think you can neglect this one because
142.
I mean,
Because the
see,
one,
they should not give none of the above here. Okay, that is
okay,
confusing. I
yeah,
accept it because if you give that, then that is also correct answer, right?
yes,
So I think this is the correct answer. Four nine
yeah,
three seven four three.
yeah.
So uh, now we have to see what is given in the solution because, like, I mean, if you don't want to be so strict, the A option is correct only. But
Yes, sir.
I get your point. None of the above
Um,
also
I
makes sense.
already have submitted the assignment and I have selected a option there.
Yeah, but this type of confusing thing should not be there.
Yeah,
Anyway, so I think it's safer to go with A.
yeah.
Uh, if not, let me know. We'll see if we can get anything. Okay.
Okay.
Anything else, Narendra?
Yes, today you have given the concept of heat source with a finite heat capacity. It's any too good
Yeah, I mean, in
because we
real,
because we have solved most lot of any problems with a finite heat source and the heat sink.
infinite, no?
Yeah, infinite.
That is
Mm.
typical, but
Thank you very much, sir. याने you have taken us the problem, different any problem.
mm, But actually, this problem is interesting. This in which
Yeah,
both are na?
both are finite.
But you need some extra concept of this entropy change and all. So maybe
Yeah,
not at this point, but
yeah,
later remind me once if I forget.
yeah,
Uh,
yes.
we can do that also. I
Okay,
think professor also can take this. I mean, if
yeah.
not, then we'll do. Okay.
Okay, sir.
Okay. Anybody else? Rishabh, Priyanka, anything you want to ask, or I can see only uh, two are there. Rishabh and Priyanka are there. Yeah. Anything, Priyanka, Rishabh, or should we close for today? If you don't answer, I'll think you know everything about this topic, and we'll go our way.
Okay, sir. Thank you very much.
Okay, Narendra. Have a good
Yeah.
night. We'll
Okay, good night, sir.
meet next Tuesday.
Okay, sir. Definitely.
Okay. I think Priyanka and Rishabh are not answering, so I'll wait for.
Yes, sir.
Okay, Rishabh is there. So everything is good, Rishabh. I mean, any doubt or anything? Fine.
Yes, sir. So your concepts are sir, when we got about concept of finite thing, finite
Mhm.
that is very new concept to us.
Okay. Yeah. So maybe we'll discuss about this more next time. At this point, you are not. I mean, I am assuming whatever is taught in the class, that much you know. So you need some extra things to solve such finite heat capacity problems. But maybe next time we'll discuss. Okay.
Yes.
Okay then. Priyanka, you want to say something or fine? Hello. I'm not able to listen. Maybe. Uh, are you able to speak up, Priyanka? I mean, I'm not hearing anything from your side. Hmm. If you are not able to speak, you can type also. I think. Is there any option of chat in this meeting? Oh, there is some audio issue. It shows. Anyway, so Priyanka, if you have anything, maybe next time we can talk. It's getting late now. So yeah, I think I'll close now and see you all. Thank you for joining today and see you all next time. Okay. Yeah, yeah, I got the message now. No doubts. Okay, Priyanka. Okay. Bye then, everybody. I'll close the meeting now. You can leave. Thank you.